Good morning students, and today we can see the Cauchy integral formula and Cauchy residue theorem. First let us see the statement of Cauchy integral theorem. If f of z is analytic, and f dash of z is continuous inside and on a simple closed curve C, inside and on a simple closed curve C, then line integral over C f of z dz equal to 0. So this one we call it as a Cauchy integral theorem. So next we can see the Cauchy integral formula. What do you mean by Cauchy integral formula and how will you apply in the problems? The Cauchy integral formula statement is if f of z is analytic within and on a simple closed curve C, and z naught is any point inside the curve C, then how will you find out the point? Means your f of z naught is 1 by 2 pi I line integral over C f of z by z minus z naught dz, and here the integration around C is taken in the positive sense. Now let us see one example in this type. So how will you find out the value of this function? Evaluate cos pi z squared by z minus 1 into z minus 2 dz, and here where C is the circle, mod z equal to 3. Since the denominator is a product, so you have to apply the partial fraction method. I hope all of you know how to apply the partial fractions method. So here you can split it as a by z minus 1 plus b by z minus 2, and taking the LCM, z minus 2 plus b into z minus 1, and you have two equations. By equating the z component on both sides, you'll be having a plus b equal to 0, and equating the constant on both sides, you have minus 2a minus b equal to 1. On solving both the equations, we are getting it as a equal to minus 1 and b equal to 1. Now let us see how will you apply that. So you can rewrite this 1 by z minus 1 into z minus 2 as minus 1 by z minus 1 and plus 1 by, I am applying the values of a and b. So therefore the line integral over C cos pi z squared by z minus 1 into z minus 2 can be rewritten as dz, can be rewritten as cos pi z squared by z minus 2 dz minus cos pi z squared by z minus 1 dz, and here your f of z is cos pi z squared. Okay, and here by equating the denominator to 0, you have z naught equal to 1 comma 2, and both the points 1 and 2 lies inside the circle mod z equal to 3. So next, how will you apply the Cauchy integral formula? So according to the formula, when you want to find out the value, you have to bring that 2 pi I to that side. So when I do like that, it is 2 pi I into f of 2 minus 2 pi I into f of 1. Already you know that f of z is cos pi z squared. So your f of 2 is cos 4 pi, and the value of cos 4 pi is 1, as cos n pi equal to minus 1 the whole power n. your f of 1 is cos pi, which is minus 1. So therefore applying that, you will be having 2 pi I into 1 minus of minus 1 is 2. Therefore the answer is 4 pi I. So this is how you apply the Cauchy integral formula. Next, when you have the denominator greater than 1, then how will you find out? So that becomes a Cauchy integral formula for derivatives. In that case, your formula becomes fn of a equal to n factorial by 2 pi I line integral over c f of z by z minus a the whole power n plus 1 dz, where a is the point lying inside c. So now let us see one example in this type. Evaluate line integral over c z e power z by z minus a the whole cube dz. So here you have your f of z as z into e power z, and you have that n is equal to n plus 1 equal to 3, therefore n equal to 2. So therefore you have to find out up to second derivative. You have your f of z is equal to z e power z, and your f dash of z is e power z plus z e power z. I am taking the applying the by that is product rule. F double dash of z is e power z plus, again I am applying the product rule, e power z plus z e power z, and is a is a point lying inside. So let us find out that f double dash of a also. So e power a plus e power a plus a into e power a, that is a e power a plus 2 e power a. Now applying the formula z e power z by z minus a the whole cube dz, after applying the formula it is 2 pi I by 2 factorial into f double dash of a, and what is that value means, that is e power a pi I into a plus 2. So this is the case when you have the degree as greater than 1. Next we will move on to Cauchy residue theorem. So now Cauchy residue theorem states that is you have to find out the residues at the poles. So the formula is, if f of z is analytic at all points inside and on a simple closed curve C except at a finite number of poles, then line integral over C f of z dz is 2 pi I into sum of the residues of f of z at its poles. Let us see one simple example in this type. So evaluate line integral over c z minus 1 by z plus 1 the whole square into z minus 2 dz, where c is the circle modulus of z minus I equal to 2. Now you have to consider two components here, and what is that means? First one, by equating the denominator to 0, z equal to minus 1 is a multiple pole. Of order 2, and z equal to 2 is a simple pole. And here modulus of, by putting a z equal to x plus I by minus I equal to 2. So here it is a circle with center 0, 1 and radius 2. And now, since here the 2, 0 lies outside the circle modulus of z minus I equal to 2, so the residue of f of z at z equal to 2 is 0. Since 2, 0 lies outside, if it lies inside means then we can find out the residues. Lies outside the circle modulus of z minus I equal to 2. Now next step, you have to find out the residue of f of z at z equal to minus 1, and here it is a multiple pole. Applying the multiple pole formula, limit z tends to minus 1 by 1 factorial d by dz of z plus 1 the whole square into f of z. Now limit z tends to minus 1 d by dz of z plus 1 the whole squared. Your f of z is z minus 1 by z plus 1 the whole square into z minus 2. I can cancel this one, and after differentiating I am getting that limit z tends to minus 1 d by dz of z minus 1 by z minus 2, and after doing the differentiation applying u by v method, I am putting z equal to minus 1, the residue is minus 1 by 9. Next apply the Cauchy residue theorem. By applying the Cauchy residue theorem, that is 2 pi I into sum of the residues, you will be having that 2 pi I into minus 1 by 9, it is minus 2 pi I by 9. So this is how you apply the Cauchy residue theorem. Thank you, students.